Hello and welcome everyone to this podcast for epigenetics. In this podcast, we're going to talk about cell differentiation. From zygote to a fully differentiated cell. If you remember, last time we talked about the germline. We ended talking about the germline, how it was set, and then how that would go on to make spermatogonium or oogonium, depending upon the sex of the individual. And we talked about how the epigenetic programming was reset in these cells so that it would be properly imprinted. So both spermatogonium and oogonium maintain the sex-specific imprinting. They would then go on to produce the sperm, or the egg, or oocyte, I should say. That could then be used for fertilization to produce the zygote. And we talked a little bit last time about how that zygote goes on throughout the pathway to be demethylated and then remethylated. But what we're going to do in this podcast is we're going to pick up on this zygote again. And we're going to talk in more detail about how the zygote goes on to form a differentiated cell. So as we begin this discussion, I want to start off by thinking about fully differentiated cells. So here's a picture. This is of course a picture of one of my sons. They love it when I use pictures of them in podcasts and lectures. And it's interesting to think about how every one of the cells in his body, the trillions of cells that are in his body, contains all the genetic information that's necessary to go from zygote to adult. But clearly, any one of these cells right now is very differentiated. Now, when you think about these differentiated cells, when did they become differentiated? Well, we can look at a much earlier picture of Peyton, shown here, when he was first born. This one's Peyton, of course. This one is some dude. But all the cells, well, at least most of the cells in Peyton as a baby, are fully differentiated. Certainly he has some stem cells, and certainly the old Peyton here has some stem cells, lots of stem cells, in fact. But most of the cells have been differentiated. In fact, really, differentiation between 5-minute-old Peyton and 16-year-old Peyton, that differentiation hasn't changed a whole lot. Certainly there's been some changes, but not much. Most of that's already set here. So we have to go back even further to understand where that slate was originally made. Now luckily, because of the kinds of technology that were available, we were able to get pictures of Peyton from a much earlier stage, as you can see here. Okay, that's not even remotely true. But wouldn't it be cool if it was? These are just pictures I took from a textbook. But, as we see here, this is our blastocyst. And we can pretend it's Peyton's blastocyst. And here is a stage that we call the morula stage. Here is a 4-cell stage. Here's a 2-cell stage. And here's our 1-cell stage. Now, at each of these stages, there are different degrees of differentiation that have already occurred. In the blastocyst stage, we're going to learn in a moment that cells have differentiated. But as you look from the 1-cell stage to the morula stage, there's really no differentiation. Those cells are all about equally programmed. So what happens between this 1-cell stage as we move forward through development to form a baby and then ultimately an adult? Well, he thinks he's an adult, so I'll give him that credit. So what we're going to do now is we're going to reverse this, and I'm going to start off by talking about this 1-cell embryo. But before I remove all the pictures, I want to make one quick point here. As we think about differentiation, moving in this direction, I want to write down here a mantra that we should remember. Differentiation is unidirectional. Once a cell becomes differentiated, there's no going back to an undifferentiated state. Usually. We'll learn later, not in this class, in other classes, you'll learn that cancers are often set by a de-differentiation of cells. But under normal healthy conditions, differentiation is unidirectional. So let's go ahead and write that up here top, just to keep in mind. Differentiation is unidirectional. So let's start off with our one-cell embryo. And as the picture you just saw just recently, it would make one of this first division, and it would be the two-cell embryo. These cells at this stage here we call blastomeres. And then, of course, we have the four-cell embryo. And then a few divisions later, we end up with the morula, this ball of cells here. The morula stage here contains about 16 cells. One interesting thing is that this embryo here at the morula stage isn't that much bigger than the one or two cell embryo. And that's largely because of a very shortened G1 and G2 stage during early embryonic cell divisions. At this stage, though, there will be some cells, I'm just going to put an orange mark on them, that will slowly move towards the outside of this embryo. Now, these outside cells, they're going to become trophoblast cells. And let me write that down here. Trophoblast cells will become the extra embryonic membranes. These include the amnion, the allantois, the yolk sac, and the chorion. Some of these will go on to form the placenta and the amniotic sac. Early blood cells will also come from this area as well, but they do not become the embryo. These become supporting structures of the embryo. So let's draw them like so. These are the trophoblast cells. And these other cells will go on to form this structure here. And this is known as the inner cell mass, which we'll often just refer to as ICM. So in here we'll have all these cells. These cells in the inner cell mass will become the embryo. This is what we refer to as embryonic stem cells. This new structure here we call the blastocyst. This marks the first stage of cellular differentiation. Okay, we have just described the process of going from one cell embryo to a blastocyst, and how at this stage here between morula to blastocyst we undergo a differentiation. In thinking about these cells in this process, I'm going to introduce two important terms. The first term is totipotent cells. The cells, all of these cells, from one cell embryo to the morula cell, the 16-cell stage, are totipotent cells. Totipotent cells have the most potential. If it helps you remember, you can think of it as total potential to become any cell. They can become the inner mass cells, they can become the blastocyst cells, they can become anything. And so in human embryonic development, that lasts from day 1 to day 4. That's the only time period that they exist. These cells here are pre-implantation. Okay, now the second term I want to bring up are pluripotent cells. So they have the potential to become embryonic cells. That would be the inner cell mass cells, have the potential to become that, or they have the potential to become those extra embryonic membranes that will then form the amnion and the placenta. However, pluripotent cells, under normal circumstances, cannot become totipotent cells. Remember, because differentiation is unidirectional. So they're not going to go back this way. This is probably a good thing. In fact, it is a good thing. It should also remind you that it is this inner cell mass that are the embryonic stem cells. When we hear embryonic stem cells, that's what we're talking about. Now, I've ran out of room, but I want to point out that, and I'll just write it over here, kind of make an ugly little blip over here. These cells, these embryonic stem cells, are only embryonic stem cells for days. So a very short period of time when embryonic stem cells actually exist in the embryo. And then I want to say that this blastocyst embryo, towards the end of the blastocyst stage, implants in the uterine lining. So going from totipotent cells to pluripotent cells marks this first stage of cellular differentiation. So let's pick up the story from our blastocyst here. During late blastocyst development, it will implant in the uterine lining, as I mentioned on the last whiteboard. And as it implants, it goes through this process called gastrulation. And gastrulation is all about what's happening to this inner cell mass, and it will mark our second stage of cellular differentiation. So let's draw here what gastrulation looks like. As you can see, the trophoblast cells don't change, but what does change are these inner mass cells. They go through this second stage of differentiation, where the cells will become one of three types of cells. These cells up here, which I'm going to mark with an A, just for a key, and so those A cells here, these are the ectoderm cells. Ectoderm cells will go on to become a variety of cells, including skin cells and neurons. Cells here in the middle, B, are called the mesoderm cells. The mesoderm will go on to form a variety of muscles and connective tissues, as well as some other tissues as well. And lastly, on the bottom here, I'll put C. These become the endoderm. Endoderm becomes our gastrointestinal tract, including pancreas, liver, and all the organs of, or at least most of the organs of the GI tract. They also become respiratory tract, auditory tract, and other tissues as well, but these are the main ones. All of these cells in the ectoderm, mesoderm, and endoderm are what we call multipotent cells. They have the potential to become, for the ectoderm, skin cells or neurons, mesoderm, muscles and connective tissues, endoderm, GI cells, respiratory cells, and auditory cells, as well as others. So even at this very stage here, very early stage of embryonic development, we no longer have embryonic stem cells. These are multipotent stem cells, which we also call adult stem cells or somatic stem cells. I really dislike the term adult stem cells because it implies that they're only found in adults. But these somatic stem cells exist in a very early embryo and continue to exist throughout embryonic development into childhood and adulthood. So I really think the term somatic stem cell is the most appropriate because these cells go on to form somatic cells. Now again, remember, differentiation is unidirectional. These multipotent stem cells here cannot go back and become pluripotent or totipotent stem cells under usual circumstances. Okay, I think that ends this podcast. In this podcast, just remember, we started with a one-celled embryo, and we took it through several divisions until we ended up with the blastocyst. And we talked about various features here, but the key point here was that this is the site where the cells went through their first cellular differentiation, where they went from totipotent stem cells to pluripotent stem cells. And then we took it one extra step here to the gastrulus stage. And in this gastrulus stage, remember, we formed 3 layers of cells that were all multipotent stem cells. So we went from pluripotent to multipotent stem cells. And these, again, remember, were the ectoderm, the mesoderm, and the endoderm, and how these would continue to develop into fully differentiated cells. In the next podcast, what we're going to want to focus on is how we maintain cells in this pluripotent state, and then what happens in the cells to allow them to move on to the gastrulate stage and the multipotent stem cells. And then at the end of the next podcast, we'll talk about these layers here, and I'll give a couple examples of how they can differentiate into their terminal differentiated cells. All right, if you have any questions about the information on this podcast, please make sure you come see me. If not, I'll see you in class. Bye.